Hello, everyone. Today we're going to be talking about mean time to recovery, but it's not going to be the mean time to recovery of our systems. Rather, it's going to be the mean time to recovery of us, the engineers. How long does it take us to recover from an on-call shift? And have you been able to truly relax when waiting for a possible emergency for a week, 24/7, looking at your phone, wondering, do I have the next 15 minutes free or is this thing going to go off? Businesses, I think, are a bit obsessed with availability. They're chasing the nines, 99.9, 99.99, and maybe even more. While we all aim for well-architected systems with redundant infrastructure, auto-scaling, self-healing, retries, backups, and so on, things can and still will fail. And when they do, that pressure is on the engineers. Highly available systems appear to require highly available engineers in some cases. For many of us, that means on-call means always being ready and always worrying. Many of us don't work for the big tech companies. And even if we did, it doesn't mean we're well set up for on-call. Not all teams are large enough to provide rotas that are sustainable. We don't have people in different time zones to allow for business hours on-call only. For many engineers, being on-call means always being ready to work, not sleeping and worrying about what problems might happen. Their life is essentially on pause for the on-call shift. As such, even when nothing goes wrong, on-call is really stressful. Over time, this can make engineers burn out, dislike their job, get sick, and quit. So what does recovery from on-call look like? How long does it take an engineer to recover from on-call? And do they have enough time between the different shifts to do this? I think the ideal cycle is as follows. It starts with the on-call shift. The engineer is alert, they're responsive, active on Slack, looking at all the things coming in. They know what's going on. But once it ends, it's over. They can fully disconnect, they can put their phone away, they don't need to be looking at it, they can recharge, they can get back to their standard life routine. But once recharged, I think it's important to give them time to reflect and wonder what could have gone better, both work-wise and how they handle the responsibility personally of being on call. It's important that they take these reflections and constantly improve the process for themselves and for everyone else involved. And then they have to do it all over again. They have to shuffle their schedules, check their system access, check that their paging app still works. Happy, well-rested engineers create reliable systems. And yes, outages cost money, but unhappy, stressed engineers are just as damaging for the business. I think this is where managers play their crucial role. They need to ensure that we have sane team sizes to allow for sustainable rotas. They need to create happy, high-trust environments. We should know as engineers that if we miss a page, we're not going to be faced with a disciplinary hearing or something. We need to know that they accept that risk. And we need to know that on-call systems, just like our proper systems, need to have redundancy in place too. And lastly, and most importantly, they need to say no to unreasonable expectations and protect the team at all costs. Optimizing for uptime, availability, and mean time to recovery is important, but not at the cost of our well-being. We need to build resilient systems, but we also need to build resilient teams. Thank you.
This is Roberto, and I'm here to tell you everything you need to know about rollout monitoring at scale. So I work on the GC VM SRE team, which is responsible for the health of the many virtual machines that are managed by Compute Engine. And topologically, there's many virtual machines on many physical hosts, on many zones and many regions. You see where this is going. It may not be very evident, but everything you've just seen requires rollouts. And when you need to do rollouts to hypervisors, kernels, on more than like 100 zones, this is a hard problem and must be done carefully, because even with very rigorous testing, bugs can slip through. So we want to protect customers quickly and faster than an SRE getting paged and manually stopping the rollout and fix the problem. And to do that, well, in the 1900s, canaries in coal mines saved lives by providing advance warning of toxic gases. And in the 2000, released Canarying saving customers and SREs by rolling out changes on a small scale first and then continuously checking for health signals on the updated population. You see that on the right-hand side. Control group is the old version, canary group is the new version. Now, here's how that looks in practice. After we qualify and test the release in pre-production, we start rolling it out to internal workloads first, small parts at a time. We continuously check if anything is bad. And if we do detect that, we stop the rollout and a human is summoned to investigate. Beautiful. Of course, all the glitters is not gold. Everyone that's ever done canarying will tell you it's very hard. For example, here's how a signal used in canarying may look like. If you assume higher is better, as a human, it's very easy to tell that red is worse, canary is worse. But for a machine, like how do you actually do it? Do you do it a threshold? It may look good, but then you're just ignoring the control signal. You're losing value. And then if you need to choose a window, right, what window do you choose? If you choose a small one, you just miss content, you miss context, right? So some of those problems can be solved by everyone's favorite, statistics. The solution is simply to use equivalence testing. You establish a null hypothesis that control and canary groups are similar, and you prove whether this is true or false with a certain significance. You use p-values to provide significance levels, and you can use different statistical functions depending on the value that you have, like binomial or t-tests. Now, in GCE, we had lots of problems because we are not really a normal RPC service. We have many VMs, right? We're working with VMs, and specifically more than 20 machine families, and many teams shipping changes to those. So there is no real individual metric that we can use for that. So instead, VMs can self-diagnose problems, and we use the signal for canarying, as well as having specific specialized checks like using crashes and vCPU wait time, as well as other like accelerator optimized VMs. Also, the fact that we have a large number of VMs makes it necessary to pre-aggregate signals for canarying. So we need to have very good debugging workflows for engineers to be able to figure out what is actually exploding. And last but not least, of course, I'm just kidding. Last but not least, VMs run customer workloads. So those are very diverse, and we need to make sure that the signals are workload agnostic and that we don't just stop the rollouts if we get a specific VM that is causing a lot of vCPU wait time, for example. So with great challenges comes great opportunities. Canarying GC has already prevented a lot of regressions from affecting our customers. To make it even better now, we're moving to a model where individual developer teams will provide signals for their subsystems, collaborating to SRE to maximize coverage. And this is actually very important when we have such a large surface area. All right, so that was a run. TLDR, should you invest in canarying? Absolutely, don't delay, canary today. Thank you so much. If you're interested in more, please take a look at the QR code.
Hello, good afternoon, good evening. I'm Konstantinos from Skroutz. I'm an SRE tech lead in the SRE organization at Skroutz. If you are not aware, Skroutz is the leading e-commerce marketplace platform in Southern Europe with more than 1.5 million active users and more than 45K orders per day. And so why I'm here? I'm here to tell you a story about a 4-month project which was conceived as the unknown factor in all our SRE equations regarding the cloud migration journey. And I'm going to share you, I'm trying to distill it in 4 minutes along with the gist of what we learned along the way. So this is about our RDBMS cluster based on MariaDB, which was running on an EOL version and how we upgraded it to an LTS one. The cluster has as many instances as the cute little monsters up in the right. It was running on an EOL version, and we were tasked with upgrading it. So it was like a cocktail-like cluster. It was running, some of the instances were running on the cloud, some of the instances were running in on-prem, and it was multi-version. MariaDB allows it, so we did it for different use cases. It was running on different configuration and on different hardware nodes. So how we did it? How we broke the EOL chains? We tested extensively. We read our switchover tooling code more than twice. We even diagrammed it. We authored a 25-page runbook. We sharpened our tools, performance engineering tools, and one day we all gathered in an incident channel and we switched it over. Was that easy? No. In fact, we had to switch over twice. But here we are, stable again. Running on an LTS version and with a couple of bug reports filed upstream. Next up, we plan to do more switchovers, break more EOL chains, and hopefully this journey will lead us back to you next year. And if you ask me, the most important lesson that we learned along that way was that no matter how descriptive your map is, no matter how sharpened your tools are, You need sometimes to be driven by the circumstances and foster confidence, and this will make teamwork and collaboration flourish inside your team. Thank you.
Hello, my name is John Lunney. I'm the SRE lead for Workspace AI at Google. We launched new products in Workspace that are based on LLMs. We did it in 67 days. It was pretty chaotic, but we learned a lot. And after 15 years at Google, actually I started to get interested in what is new in SRE rather than just what we already knew. We heard from Todd earlier today about what generative AI is and how it works, how it doesn't work. This talk is not about that. This is about the SRE work around the topic. So you've heard a lot about it. You've heard about ChatGPT. You heard that you must have an LLM feature launched this year or the board is going to be very unhappy. What is different about these? The cost per query is very high. That's the first thing SREs see. It's also very competitive in the industry today. So we're changing the products very fast. New product comes out. You saw Notebook LM from Google, very popular. Suddenly everyone wants to do that. It's a big change. So what do you do about this? You need to work faster, but also in lockstep with the teams that are in other parts of the company, which you maybe ignored before. You don't need to be a maths expert. You don't need to do a huge amount of statistics. You can learn how these models work. That's very interesting. Having some sort of mental model of how they work is extremely useful, but you don't need to learn it in detail to be useful in the product. What is important here is actually how quickly you can cycle through product improvements. Because you're building these products on top of foundation models, which are sort of generally good at language, and then you have to tailor the model somehow in various ways to make your product work. And that involves a lot of data collection, fine-tuning, gathering feedback, feeding that back into the system. It's very easy to build a prototype on LLMs. You can get something out the door in a day, in a hackathon. To turn that into a product that you can launch or even sell or have people pay for is extremely hard. And Todd is nodding in the corner. This reliability, scalability, these are the things that make it hard. Having it be consistently decent quality is even harder than those. So traditional SRE skills are not finished with. These are very relevant. I think it's good news for everyone here. It made me more excited about the job again. What's different in this world? Well, at least in the hyperscalers, the big tech companies, we got used to the idea that resources, so machines they're not quite free, but they're pretty cheap and you can get them if you need them. It's very elastic. This is not the case for accelerators. Everyone in the world is trying to get the accelerators as fast as they can. You're up against them. You have to predict in advance how many you're going to need, because if you're not using them well, then someone else in your company is losing money daily. So you need to do planning for your features. It's very hard to know how much they're going to cost. There's a whole new world starting here. How I think about this, maybe as a sort of a metaphor that you can take away, think about these LLMs, so the model, the language model that you're serving off, as a kind of very expensive database that underpins your product. And it's very slow, it's very expensive. It's basically a really annoying dependency. Think about it that way, and that will give you some of the protections that you need to put in place. You probably need to be thinking about caching. You need to understand, to some extent, how it works. That also means that traffic shaping, shedding, DOS attacks are suddenly a very big deal, because each of these queries doesn't cost like millicents. They cost potentially dollars, and it can be very expensive for your company. It can also be impactful to your real customers if you're letting in DOS attacks. So I would say build in abuse detection from the start and think about how you're going to prioritize traffic between different types of either queries or users or features, so that you're not spending all of your little dollars on what you can. Releases and rollouts are still very, very basic. You will need to learn a lot to just push the model, but there's very little automation. SLOs, total new world. And I would say thank you.
Hey, this is David Nowak. I'm working for Huawei Research Lab here in Dublin. We are a research lab, so we have certain freedom to innovate and make cool things. And as such, we decided to rewrite Envoy proxy in Rust. We spent about 6 months on it. And this is the journey that we went through. The rationale is very simple. Envoy is written C++. Most of the security vulnerabilities are due to memory corruption. There is a list of CVEs for Envoy and Nginx and Rust. So Rust gives us this, well, nice warm feeling, fuzzy feeling that it is better than, or safer than everything else. It's a busy crowd now, a busy space. There is a Cloudflare doing stuff with the proxies. There is Pingora. There is obviously Google, Microsoft, and everybody else moving Rust into the kernel. The objective that we had in mind was to make it a one-to-one replacement for Istio proxy. So at the API level, you can just slot it in using XDS protocol and configure the Orion proxy, as we call it, similar to what you would do with Envoy. We support at the moment HTTP, HTTP2. We FIPS compliant because we're using boring the Rust LS, which is now certified. This is the architecture. We share nothing. It's very fast. So we have Linux threads running Tokyo runtime. That's your running Hyper. So all the components are taken from the open source, off the shelf. We didn't really modify much. We added loads of glue to glue them together. And we added this orange box, which is routing and filtering. We've brought it for the run using this environment here, which is completely unrepeatable, but it gives us consistency of the runs. So here are the figures. If you look carefully, the trend shows that we are faster than Envoy and scale with the CPUs. We're not as fast as NGINX for the HTTP. We are though faster when we use TLS because NGINX is still using OpenSSL. Same figures, just in the relative performance, so we can see how was the difference in between the implementations. So what are we planning on doing next? So we're going through our headquarters to get it to the open source, to open source it on GitHub, so everybody could contribute, have a look, check it out, and tell us what they think about it. We believe it could be an alternative for Istio proxy, for example, in the cloud-native environments. So we are polishing, adding extra features, metrics, things like that, and working hard to get it open source. Thank you.
Excellent. Hello, great to be back. I should go on to the next one, and there we go. Okay, so I spent the last few years thinking a lot about cost management, mostly in a Kubernetes environment, but not exclusively, and how SREs can help with this. So I put through a slightly buggy slide deck. So most importantly, what drives Kubernetes waste? After digging into it, one of the ones I couldn't believe was that in Kubernetes, by default, the threshold for scaling is 10%. So if it thinks you wanted 100 pods, but now you've got extra load, and now I'd need to give you 109 to make sure your service is happy, I'll do nothing. It waits until you need 110, and then it adds another one. So from straight off, you need to add 10% extra capacity for this tolerance idea in scaling with Kubernetes. The next one that you'll need is, well, everyone knows that scaling delays exist. If you want an extra pod, maybe you get it in 10 seconds. If you want an extra node, maybe it takes 60 seconds. If you want 100 nodes, it's going to take a while. So it's really, really important for services to have a certain amount of padding based on how much they scale up. And it's helpful if SREs are monitoring how long it takes to scale up. Like, what percentage of the time when you ask Google for 100 nodes, do they go, I'll give you 20? Because it does happen, right? You don't get everything you want all of the time. When you have a scale-up incident, everyone else is having a scale-up incident at the same time. Another big problem, you might not have thought about this, is mixing state and statelessness. You might think that Redis or Spark jobs aren't really stateful, but if you start evicting them with no notice, listen for the screams of their owners. When you scale stateless workloads down, great. They go away, but you might have a bunch of stateful workloads mixed in, and a single stateful workload can hold on to a node for days, weeks sometimes, wasting a huge amount of resources. So yeah, we're going to lose some on that. The next idea could be, we should just deploy new clusters or maybe new node pools for our stateless workloads or other ones. No, don't waste time creating new silos in your company just because you're too scared to have a difficult conversation. Go ask the Spark team, how about you checkpoint your Spark jobs so I can shut them down within 10 minutes? Do that instead. You may also have noisy neighbors. I hope you enjoyed Ben and Rene's talk earlier on. It's really fantastic. If you missed it, definitely go watch the thing. But you will have noisy neighbors, right? It's not unusual for the 99th percentile usage to be about half of the 100th percentile usage of a service. Case users often exclaim, it's cool, we can turn off all our CPU limits, we live free, throw all our clothes off and go live in the woods. It's liberating to live without clothes, but your coworkers can get uncomfortable. So if 1% of the time you need an extra core or two, that's fine. But if all of your neighbors have the same idea and you actually all need 10 or 20 or 40% more resources, then everyone's just going to get the resources they requested and we're stuck. So yes, we absolutely know that we're going to have noisy neighbors. We're going to pad out a little bit there as well. This is just on the infrastructure side. This is not the application is crap. This is the infrastructure is crap. And this is the best we can do. Finance are unhappy, and yeah, it's more common than you'd realize. So what can we do? SRE superpower, SLOs, right? So tell people, we promise we will get your pod scheduled in X seconds, 99% of the time, something like that. And go measure it and make a promise on it, make an SLO. Certain percentage of the time, you're going to be within your scaling target. So if someone needs 110 pods with 50 cores each, don't worry about it. We will get you there and it'll be fine. Measure it, prove it. And the last and really, really important one here is measure how much free capacity there is on each node, because if you run out, you're boned. And I'll leave you there with the customer side of the SLOs, which are also really important.
All right, so hi everyone, I'm Jennifer Petoff, and I'm going to show you how to SRE anything with some constructs for using SRE principles to work smarter and live better. So the software development lifecycle can be used to explain how to apply SRE principles to anything. So the what is the thing that you want to achieve, the how is the SRE aspect. And to apply these concepts to other things, you just need to define the domain, the thing, and the means to get there. So for example, I lead learning programs, and in this case, the domain is training programs, the thing is training content, and the means to get there is deploying a consistent and reliable training program that meets the needs of our students. For domain running a restaurant, the what is the menu, the how is taking orders, delivering food, and accepting payments in a timely manner to keep our diners happy. And so it goes with customer service too. So in all three examples, the focus is on satisfaction, not perfection, because as we all know, 100% is the wrong reliability target for basically everything. A goal of perfection also stifles innovation. So SRE is about achieving balance between competing concerns. So this lets us move fast when things are good and respond to failure appropriately when it happens. So when you think about SREing anything, think about the appropriate trade-offs between reliability, time, velocity, and cost. So is more effort always better? No. If you go above and beyond the happiness threshold, you're wasting time and effort that could be applied better to other things. So what are the SRE principles and patterns that we should abide by adapted to anything? So first of all, users should never notice a problem before you do. Develop solutions to eliminate classes of errors rather than being satisfied with point fixes. Don't build the thing with human toil. And failure is an opportunity to improve, not to brandish pitchforks. So a big aha moment for me was realizing that the elements of the service reliability hierarchy could be adapted to the training context, and in fact, equally well to a multitude of domains. So the items in green here, they're your aspirations. So envisioning what you're trying to achieve and how you'll know if the thing and the domain are fully actualized. Underpinning this in blue, we have diagnostic questions that we can use to enumerate possible tactics to achieve that aspiration. So mind your lottery factor. So a lottery factor of 1 means that if someone were to win the lottery and quit tomorrow, you'd be left with a gap. You have a single point of failure. So make sure people are cross-trained in different areas, ensure your documentation is up to date, and explicitly factor this in as you think about what could go wrong. So now let's apply SRE to life situations. So I wrote about how I applied SRE principles to deal with a family medical emergency. And another example, I applied SRE goodness when faced with a travel emergency. And I invite you to check out these examples of SREing anything using these bit.ly links. So what about SRE for well-being? So it turns out capacity planning and load shedding are actually great life hacks. So SREs build a capacity plan and provision a service to run optimally. And if the service reaches capacity, at best, service degrades. At worst, you get a cascading failure and a total outage. So to protect well-being, I use a similar construct. I limit time spent on things that I love but are not necessarily rewarded. And I set aside a quota for these activities. And when capacity is reached, I start saying no. Load shedding. I set quotas for various aspects of my life, work, family, fun. And when unexpected demands arise, I load shed by temporarily reducing non-essential activities in other areas. And this approach helps me to avoid burnout and effectively manage competing priorities. So what have we learned? So we have learned that the what and the how are equally important. The domain plus the thing plus the means to get there is a winning combination that unlocks the ability to SRE anything. The service reliability hierarchy is a useful rubric for applying SRE principles to any situation in work and life for well-being. Yay! 0.
Hi everybody, I'm Furino and this is 9 SLIs on my. We're all on a golden path towards achieving reliability. After multiple years working and coaching teams to implement SLOs, it's becoming clearer to me that teams often struggle adopting a reliability culture specifically because they struggle with finding the right SLIs. The 4 golden signals, I feel these are mostly accurate and correct, but they tend to be extremely generic. I view these as units for a base idea, but they often must be partnered with additional concept, expectation, or use case in order to provide additional value and insight. In 2021, Niall Murphy gave a keynote at SREcon encouraging reliability practitioners to start pushing forward some new ideas of reliability and SRE. It's in this spirit I'm proposing we start thinking about SLIs somewhat differently and a step bit outside the land of SRE and engineering. Don't all reliability folks love 9s? We'll break this talk up into 3 groups of 3 SLIs that focus on learning something different about your system. The first group is the traditional guidance, the no-brainer approach. It's about emotion and asking ourselves, how does our user base feel? How do they experience our software? Application metrics are values that measure our customer and user experiences. Things to consider here are the collection of services that operate in conjunction to output something that users desire without a human intervening. There are traditional metrics that teams use when measuring SLOs to focus on availability, latency, throughput, etc. Front-end metrics are values that measure how well the UI is functioning. Common themes here around latency, elements rendering, number of content shifts, etc. However, some other items to consider include time to interaction, or how long does it take to do something the user wants, or how often does the UI crash, causing the application not to respond. Client device monitoring. This can be a bit more difficult for web applications, but it's absolutely essential for mobile, due to their hardware constraints, limitations, and variety of device models. These SLIs should be familiar to most of us when something goes not quite right on our mobile devices. Supporting services. These SLIs are initial departure from the traditional SLOs that focus on and focus more on the health of the technical systems. These items may not all be pageable, but are certainly useful into helping troubleshoot whenever issues get erased. Infrastructure metrics are values that have a relationship with the underlying infrastructure of play. There are so many examples here, but we could see some SLIs here for Apache Kafka and Kubernetes. What's key for this type of SLI is identify what the saturation point or bottleneck is for underlying workload and measure those. For network metrics, it's important to understand how well your packets are flowing on key routes and for you to understand when and where in the world you're starting to drop packets. It's also important to understand how well you're utilizing your bandwidth reservations for your cloud ingress and egress costs. The patterns for SaaS application monitoring are akin to having dependency in another service you don't control or manage. Naturally, you want to expose these metrics directly, but if that's insufficient, you have to treat it like a black box and measure the inputs and outputs of it. Management and reputation SLIs are non-traditional use cases of SLOs and error budgets, but I feel these warrant some discussion to widen the purview of telemetry to help aid in making data-driven decisions. These use cases probably aren't pageable, but they're certainly useful in helping understand when and how the expectations of the system may change. Business KPIs. It's important to understand the trajectory of your users and customer base to help inform how much load you can expect in your systems. It's generally recommended to have these SLIs remain between 2 fixed values to help determine when and where to scale up and down. There are generally accepted values for how often your company or product is mentioned on socials and how many customer support tickets are generated. However, when things start growing quickly, you need to be aware of it to help maintain your reputation. It's also a clear signal to direct customer impact. Lastly, and probably the most controversial, SLIs are those around competitive benchmarking. It's important to remember that our users set our expectations for us. If one of our competitors is overperforming in an area, or our users will eventually start expecting that from us as well. It's important to be aware of when our competitors are having an outage because you might have increased traffic. Some acknowledgements, and I will lead us with a quote from Glenn to the Good. You always have the power, my dear. You just had to learn it yourself. Thank you.
Hello everyone, my name is Robert. I'm from IBM. I'm an SRE at IBM, but I'm not going to be talking about my work. I'm talking about one of my passions, space exploration, the history of space exploration, and the lessons we as SREs can learn from the NASA engineers who did this. We were talking about the Voyager spacecraft, 2 spacecraft launched in 1977 and still working. They traveled the outer solar system, they left the solar system, they're still sending signals back. And we're going to talk a little about how they got there and how they're still working. So a little bit of history, context, early space exploration, 1959 we reached the moon, early 60s we reached the inner planets, 1972 Jupiter, Saturn in 73, and then we hit a wall. The problem is it doesn't scale. We couldn't reach the outer solar system because it's just so far away and the spacecraft weren't ready for it. The applications on the ground couldn't support it. So what do? We go to computers to solve the problem. And I have to put AI somewhere here. So this archival picture has been colorized with AI. So NASA engineers, NASA scientists using the 60s computers discovered a once in a 175-year opportunity. The planets were aligned, not astrologically, but scientifically. You could take a spacecraft, slingshot from one planet to the next, getting benefit of the speed, and then get to Neptune in 10 years instead of 25 years, which means that the requirements that you have, the scale of the capabilities, is that much lower. So they went to build the spacecraft. A spacecraft, like any system, is composed of 2 components. The functional requirements, the what and the why, for us, the business, for them, the scientific capabilities, and the non-functional requirements, the ones the SREs are responsible for. In the case of the spacecraft, it's things like the energy required, navigation capabilities, computation, communication, in short, the system resilience and reliability of the Voyager spacecraft. The miracle of Voyager is that before 1975, it was physically impossible. The technology wasn't there to build something that could get so far, to survive so far. And after 1979, it would have been too late. There would no longer be an alignment. We could not get there. So we had an alignment of the business requirements, the technological capabilities, and the opportunity. Once we get to Jupiter, you can see the difference between the non-functional pictures, the scientific ones giving us information about the moon Io, and the non-functional image, which is used for navigational purposes. They purposely overexposed the picture so they could figure out where they were flying to. But what's special about this picture is that it was created by SREs for SREs, but is actually the most significant Voyager discovery of the last 45 years, because they found out a volcano on a moon outside the Earth. This was the first time we found a dynamic system outside Earth. So the people here, are they SREs or are they scientists? This is another example of the importance of the alignment between the SREs, the application owners, the application developers. When we work together, we get much more benefit. Voyager has extreme latency today. It's 22 hours to get to Voyager 2, and the higher the latency is, the better. These are the only engineers in the world who want a higher latency, and the more latency they have, the better, because it just means that Voyager is functioning better and better. Thank you.